I'm Dr. T, and welcome to my whiteboard. So I'd like to talk a bit about gas laws and solving for variables within those equations. And so the first of the gas laws I'd like to talk about is the combined gas law. And that's going to be P1 V1 over T1 N1 equals P2 V2 over T2 N2. Now, first a caveat. I usually write my combined gas law in this fashion. Most textbooks will omit the N. They are combining Boyle's law, pressure and volume, Charles' law, volume and temperature, and Guy-Lassek's law, pressure and temperature. I like to throw in Avogadro's volume and moles. This way you have kind of the complete picture. So let's actually work with the combined gas law. By the way, there is really no need to memorize each of the individual gas laws since they are combined into the combined gas law. So let's look at a question. Let's say I have a balloon. This is before, this is after, and that's how the ones and twos are going to work. One is presumably the before some kind of change, and two is the after the aforementioned change. There are of course other scenarios, but that's the most common. So my balloon is starting out at 2.7 liters and 21 degrees Celsius. And I'd like to figure out what temperature it is if I drop that down to 1.8 liters. Now in the question, I've got a couple of explicit assumptions. I'm not talking anything about the change in pressure. So presumably pressure hasn't changed. If it did change, then you would need to at least know what the starting pressure was. Otherwise, there's no way to figure out what's going on here. And in fact, since you don't know the final temperature, you'd also need to know the final pressure. Likewise for moles, we don't know how much there is. So likewise, we need to know initial and final. But if they don't change, then we don't actually need to know what they are. As long as we can assume that P1 and P2 are the same, and N1 and N2 are the same, then using the combined gas law, we can get rid of them. See, you're looking at this, if pressure is the same, now I've got P1 and P2, if they're the same thing on opposite sides of the equal sign, then they can cancel. So it doesn't actually matter what they are. So pressure 1 and pressure 2 cancel with each other. Likewise, N1 and N2, because if we assume that they are the same, and there's no part of this question that would imply that they're not, then, hey, these guys can cancel as well. And this is one of the key assumptions to using combined gas law. I now have Charles' law, but I didn't have to memorize 4 different gas laws, only one. Well, more to come, but in this case, 4 down to 1. And now I've got the gas law that I'm actually going to use. So, algebra time. I plug in my numbers. I'm just going to use a question mark for the value I don't know. But you're saying, wait a minute, didn't he start with 21 degrees C, not 294 K? Whenever we're working with gases, we have to work in K. We cannot work in Celsius. So I'm going to take 21 degrees Celsius plus 273. That's going to give me 294 Kelvin. Now I could have 273.15, but because I don't have a significant numbers in the tenths or hundredths place for the centigrade, there's really no point. It wouldn't be significant either way. Okay, so now I've plugged in my numbers. I'm going to do the traditional divide both sides by the 1.8 liters to make that go away. And here's a trick, or I should say a trap, that a lot of students fall into. It's very easy to get to this point and say your answer is 0.0051 Kelvin. But it's not. See, that's the reciprocal. It's very tempting to stop at the reciprocal, and if you do, you get the wrong answer. So now what you need to do is take the reciprocal, make sure, because your temperature is in the denominator, and that's what's tricky here. You got to make sure that you always get your unknown out of the denominator. It needs to be on top. So I take my reciprocal, I get my 196 Kelvin, and hey, I might be done at this point, but just for show, I'm going to switch this over into Celsius and back to negative 77 Celsius, which is, shall we say, chilly. But yeah, we've got this. The key trick is figure out what's changing, what's not changing. Anything that doesn't change is simply going to get self-canceled out. And you're going to go from your combined gas law down to whichever law you need And boom, and by the way, you may very well keep all of your combined gas law. It is entirely possible you don't get to cancel anybody out in this step. It just means you got a lot more numbers down here, and you do the algebra with, once again, that warning. If you're solving for something in the denominator, then be careful. It's very tempting to stop at the reciprocal, and, well, yeah, that's not even close. So, next up, ideal gas law. Okay, let's talk ideal gas law. In this case, we're going to be utilizing all of the information about a single thing of gas and not looking at change. So for this, I'm going to need 3 of my 4 main properties of my gas. I'm going to need pressure, volume, temperature, and moles. Well, 3 of those 4. And I'm going to use this equation, PV equals nRT. Now, R is the ideal gas constant. And that is going to be this guy. Well, let me rephrase that. That is going to be this guy if your units are moles, liters, Kelvin, and atmospheres. This number will change depending on what these units are. Most of the time, you're really only going to see moles and kelvins in use. It technically doesn't have to be those two, but there's really no other popular units for those properties. But there's quite a few different units for pressure and quite a few different units for volume. So this number will change greatly depending on what these units are. So make sure they match. If they don't match, you can't use it. You're going to have to convert your units in order to get them to match. Okay, so this is actually pretty straightforward. Make sure I get that Celsius into Kelvin, otherwise I can't use it. I always have to use Kelvin for gases. I'm going to take PV equals nRT. I'm going to do some algebra on it to get the thing of interest by itself. In this case, I'm looking for the N. I'm looking for how many moles I have. I plug in my numbers and chug out my answer. Yeah, that was not hard. Okay, so the last one I want to talk about is Dalton's law of partial pressures. So in this case, if you have a mixture of gases, the total pressure, which is if you have a pressure gauge of any type, what you will be measuring, is going to be the sum of all of the individual, what we call partial pressures, or the pressure contributed from any individual gas in that mixture. The reason this is particularly important is that we could then feed this pressure into PV equals nRT and solve for, say, moles, if we wish to do so, linking these two together. Well, in this case, we have some gas that was trapped over water. So this is a common trick. You take your beaker or your vessel, you fill it completely with water, you invert it in a water bath, and then you put a tube in there and you bubble whatever gas you're collecting, in this case oxygen. Into there, the oxygen displaces the water, so the water goes down and the gas is trapped. Then you measure the pressure in here, or you just make sure the water levels are the same and you just measure the pressure outside. If the water level is the same, you know that the pressure is the same in the inside. That gives you P total. The only catch though is you're in a whole bunch of water, so you're going to have water vapor there. So what you want to do is look up the partial pressure of water at whatever temperature you happen to be at. So in this case we're at 21 degrees C, just kind of keeping that a theme. And so the partial pressure at 21 degrees C is 18.7 torr. Now pressure total is 753 torr. You don't have to use atmospheres. You got a bunch of different choices. Although for some strange reason we're looking for the final answer in atmospheres, so we're going to have to convert. But let's do the Dalton stuff first because we're already in torr. Okay, so P total once again equals the sum of your partials. That means P total is going to be P oxygen plus P water. They're both in torr, so I can do addition and subtraction right now. So I do that. If they're both in atmosphere, both in pascals, whatever I'd want, I just have to make sure they all line up as the same one in order to do addition and subtraction, which, yeah, I did. Okay. Had that weird little spot being here asking for this in atmospheres, I have my answer. It's just in torr now and has one spare sig fig. Okay, so next up, I'm going to convert this to atmospheres. So this guy, there's 760 torr in 1 atmosphere. So yeah, divide by 760, get me my answer. That's got way too many sig figs, so I'm going to go ahead and round it. And yeah, that's it. Dalton's law of partial pressure, pretty straightforward. Of course, the obvious caveat is at this point, I might very well be doing PV equals nRT with this being my P. So be forewarned that this could easily arc back onto the previous video or previous segment and be used at that point. But with that said, have a wonderful day.